I'm a postdoc from Los Alamos. This is kind of a mix-over from my PhD work on porting vector particle and cell, or VPIC, to Kokkos. It's a fairly standard kinetic particle and cell code, so you have a bunch of particles distributed on a grid, and we advance their movements based off the Maxwell equations. There's a general four-stage process. For reference, so the main computational kernel we'll be focusing on is the particle push, which in VPIC, for performance reasons, is kind of a mishmash of all of these three. It was faster fusing them, so they had to be fused, according to the developers. But yes, so VPIC 1.2 is the old original version of the code. It was originally optimized specifically for CPUs on basically every machine where the developers wanted to run. So there's somewhere hidden in the bowels of Lanel something for Roadrunner, as well as Trinity. And they essentially just ad hoc optimized the code for each new machine. And for a while, that worked fine when most of the machines were Intel. And they could get pretty good performance across all architectures in general. Unfortunately, it also means that for performance reasons, they had their own SIMD library, which took up 57% of all lines of code. And out of the 57%, only this column right here is for actual science, and it's done in triplicate. And to make matters worse, the reason Xeon Phi is specifically for 512 is because the AVX 512 implementation doesn't work on Sapphire Rapids or any of the current ones. So, yay. Obviously, that is why I ported to VPIC 2.0 with Kokkos. And essentially, it's always been taunting me because I knew how much faster VPIC 1.2. I've been side-eyeing various SIMD libraries, such as the first SIMD Kokkos library in like 2019, 2020. And yeah, so to kind of get back to where we were, we looked at 4 different vectorization strategies. So of course, just let Kokkos do what it does and have the compiler auto-vectorize everything. Give the compiler a bit of help by essentially isolating things that we know don't vectorize, and then would just break the compiler auto-vectorization for the entire kernel. Using some external SIMD library, in this case Kokkos SIMD, for manually vectorizing it. And of course, as a reference point, the ad hoc optimized custom SIMD library built specifically for VPIC. And this is just kind of an example of what it would look like with the different strategies. So you can kind of see the differences, like guided is pretty straight. It looks very verbose and a bit weird, but it is fairly straightforward. So as a kind of quick sanity check, I wanted to see what is the current status of auto-vectorization in compilers. It's been a while since I've done these tests, and I was a bit disappointed. So the runtime is normalized to the auto-vectorization. So in the ideal case, everything should be at the same exact runtime, because that would mean auto-vectorization, guided vectorization, everything the compiler is doing is getting optimal code. But even for things as simple as AXB or just introducing an exponential function kind of breaks the compiler. I'm a bit surprised how bad the reduction is. I did not expect it to be that bad. So clearly, relying on the compiler for maximum vectorization isn't something we can just do for certain codes. So this will show the results of what happens when we use auto-vectorization, so just letting it go. And yes, it performs quite badly. The users were not exactly happy seeing this performance drop. They couldn't do anything about it for a while, but I can, so I have to. So clearly this is not working. So what happens if we just give a bit of guidance? In this case, we isolate things like data loading, storing, expensive math functions that I know for a fact this will not vectorize unless you turn on fast math, as well as certain parts of the code that we know just aren't vectorization friendly. And by doing so, we can actually get really good performance for the more traditional architectures. I was very impressed that the compiler got this far. So the table on the top left essentially shows the comparison versus the auto-vectorization using the best case. So pretty close to parity for some, still pretty bad for others, but going forward, if you don't want to necessarily spend the effort of SIMD vectorizing your code, just giving it a few hints and breaking things up can get you pretty far in a lot of cases. But we still want to go faster, so let's use Kokkos SIMD. So I won't go too in-depth in explaining Kokkos SIMD because it's also very much in flux. I think the C++ 26 standard is getting released or finalized in like a week or a month or so. Yeah. So hopefully we will see, and ideally some of the things I put here will be wrong because that would make my life better. But some things that are bits, it'll provide most of the common operations, so you can treat it more or less as a regular scalar type, so it covers all the basic operators overloaded, bit masks if you need to do branching code, and something that was a bit surprising to me is that the Kokkos SIMD documents are more useful than the C++ documents online, because if you look at CPP reference, you'll likely go to the older version that has where expressions. And that's been deprecated, just removed entirely. But it's the only one that looks more complete than the actual current state of CPP reference. As for what it lacks in general, most of it is minor stuff that handles ergonomics, so typecasting for masks. If you have a mask for integers and a mask for floats, even though they're the same data type internally and same size, it doesn't implicitly cast, so it's a bit more verbose changing things. The big thing for me, at least, is permutations, interleaves, these operations where we shuffle data around in the SIMD vectors. Last I checked, it was not there. There's some proposals in the standard committee. We will see whether they get accepted, and I hope they do, because it would save me a lot of work. But yes, so in general, the Kokkos SIMD library is ready for experimentation. I wouldn't put it in production, but if you want to just test around with a few kernels to see how much you can improve and get a feel for it, go ahead. So if we parallelize the code with Kokkos SIMD, looking only at the actual compute part, so the data loading and storing is still done pretty naively, it does improve performance, but it's actually worse than just giving the compiler more information. And this is because VPIC in general is just purely memory bound, so anytime they ask us, what do you want out of the new machine? More bandwidth, more memory capacity. So we're not surprised, but if you have memory bandwidth code, just keep this in mind. Just transitioning straight to the Kokkos SIMD might not get you the performance you're looking for. So let's look at what we can do to optimize loading and storing data. Whoop, wrong direction. So there are a few challenges we have to deal with. Key among them in VPIC is that for our interpolators as well as our current accumulators, we can't guarantee the order in which we access things. So we have to assume that we will randomly access different interpolators because the interpolator we access is based on the particle. And the particles can be in whatever order. They're hopefully sorted, but no guarantees. And this means that this changes how we have to look at things for the memory layout. Accumulators in particular also have the additional bottleneck of we can write potentially to the same accumulator twice within the same SIMD lane, so we have to serialize things there. The particles look almost perfect. They are 8 32-bit types. It looks perfect for vectorizing, no padding, anything. But there's this dang integer that's messing things up. We originally tried to do stuff like reinterpret cast. It was a very bad idea. We had some very bad bugs. So for now, the cell ID is kept in its own view, which means a lot of things look uglier and have to change. As mentioned, memory layout in general is just vital for our use case. So in general, layout left is considered better when you're dealing with SIMD or GPUs because you can essentially grab, for a particular variable, you can do one load. But because we have to worry about random accesses, instead of just a load or store, we have to do gather and scatter, which even if accelerated internally by the hardware, is still slower, and in our case, that actually does matter. If you do layout right, which is more ideal for just randomly grabbing a particular structure, you can rewrite your algorithm to do a bunch, to work with vectors like this. It usually involves a lot of shuffles and is not worth the effort. So it doesn't really vectorize naturally. So what we do is just do an in-register transpose. So we just load each particular, like let's say we need to load the data at index 0, 7, 8, so out of order, potentially. And then we do an in-register transpose, so we get the data that we want to work with in the same, in the ideal format, but the actual loading and storing is more friendly to the cache and prefetcher. The biggest issue here is that without those interleaves, permutes, or operations in the in the SIMD standard, I can't do this. I have to use intrinsics. I have 6, or I think the total count is like 7 or 8 versions of the in-register transpose to handle ARM, x86 for different sizes and a few weird cases. And I really don't want to maintain that. So fingers crossed. But the upsides is that we actually get a very significant improvement in performance. So in one case for the Sapphire Rapids on DDR, we're actually already on parity, and for some of the others, we're not far off. And we actually, for once, beat the compiler. And so the error bars here aren't for different runs. It's the comparison between layout left and layout right. And in most cases, layout right with the register transpose is faster than gather and scatter. And if we use the accumulators, the gap between layout left and right actually expands in some cases. But yes, so already just vectorizing the load and store for 2 of our data structures, and we're already more or less at parity. But there's still the particles, and we should still at least look at it to see what we can go do further. So as mentioned, because of the mixture of float and int, we have a separate view for the cell ID. And that, if you're doing layout left, it's more or less fine, because with the particles, we are always we're accessing all of them in the same increasing order every time. There's no worries about random access, just load everything. Layout right also is fine. We can still use the register transpose. I just don't like having separate views for different data types. And we get very good performance. So we are at parity, and in some cases, a significant improvement over the older code, partially because the older code just doesn't outright support AVX 512 properly. But as I said, this is very ugly code, even if you exclude the register transpose. So what can we do to make things cleaner? Because the code needs to be readable and adjustable by more than just me. I have plasma physics that do the most of the development work for the algorithms. They don't like looking at this. So what we can do, at least with the particles, is start with a union. So for type punning, it is not ideal and introduces a potential undefined behavior, at least in C++. Yeah.
GCC supports this as an extension, it always will.
Yeah, so compiler-specific behavior is still not ideal. But it at least works, and we do get good performance still as well. Here, with the particles, is the only case where layout left is actually faster than layout right, and that's because we don't have to worry about random accesses. So it's nicer, but we still have horrible type punning and a landmine, essentially, just sitting there. So what we can do, wrong button, is use array of structure of arrays. So if we're doing just like reading in all the data in order, this should, in theory, be the ideal format. So we can get vectorized accesses. We can essentially help the prefetcher by having it automatically select the next variable. We are using the Cabana library for this. It also gets rid of our annoying integer float issue. So at least for the particles, this should be our ideal case. And we do get very good performance across the board. I'm still not exactly sure why Grace is so sticky, but I should not have worded it that way. But yes, so we have good performance across the board. Our code is much cleaner. The only problem is this probably doesn't work too well for the random access with the other variables. Potentially, if we mess around with the memory layout using the layout extensions for the views, we might be able to do something. But this is still a good result. I didn't expect to get this far in terms of using Kokkos SIMD to match the old code, considering the old code brought in engineers from Intel for that specific hardware just to make it go fast. Here's just a general list of weird things I encounter. So if you get your instruction, if you write your SIMD operation wrong, there's a high chance it's going to spit out basically candidates for everything, even ones that don't make sense. So even if the argument is a float SIMD, I saw messages about integer candidates. I don't know why exactly. If you're going to use Kokkos SIMD or just SIMD in general, you're going to get really familiar with the conditional function or operator in this case, because that's what you have to do for handling branching behavior. This is one thing. So this took me a while to figure out. I had to dig through a bunch of the C++ papers. So the difference between unchecked and partial essentially is that partial will do some extra memory checks to make sure you don't read or write out of memory. As it is now in the Kokkos SIMD, it basically does the same thing. That will likely change once the standard is finalized and more work can be done. There's a few weird things involving the SIMD lengths in Kokkos SIMD. One thing that kind of stood out when I was using it is that gather scatter, it closely follows the C++ 26 standard, which means it accepts only ranges rather than raw pointers, whereas everything else kind of just, you just supply it a raw pointer. It's easy to work around. It's just something you need to be aware of. It just kind of sticks out. Compiler Explorer does support Kokkos, and I was really hoping that it would support the SIMD stuff, so then I could actually see if it's SIMD vectorizing properly. Unfortunately, as far as I can tell, the SIMD length in it is set to 1. So hopefully that gets updated. And just in general, as a final message, C++ 20, the Kokkos SIMD is ready for experimentation. Feel free to throw it at a few kernels and see how it performs. Just wait a bit longer before it gets anywhere near production. But yes. So using Kokkos SIMD as well as various optimizations to the loading and storing code, we've reached performance parity with our old VPIC 1.2 code. If you don't want to go full SIMD, just massage the code a bit to help the compiler, and you can get pretty far, especially with like simple, more common architectures. I really hope interleaves and permutes get into the standard. And yeah, so in general, unless you know your code is completely compute bound, you're going to have to look at these load and store operations. So if you're interested, feel free to talk to me, especially for the register transpose. Maybe we could work on like a helper library for more advanced data loading and storing, rather than just leaving everyone to raw SIMD. Maybe as kind of similar to how Cabana is an additional helper for memory layouts. And yes, any questions?
So I just checked, and I believe that the permutations are in 26. I think they were voted in last summer. So yeah.
Okay. I wasn't. Yeah.
There's not like going to be like a feed of everything that gets added, so I'm not surprised that you didn't find out. But like, yeah. So hopefully that will be also implemented inside of the Kokkos implementation too.
Yes. Good to know, because I was just reading through their papers, and I don't know the decisions based on those papers. Yes, anything else?
So I like the on-register transpose approach very much. Do you think if AMX, matrix register, can that be used for transposing AOS to SOA also, not only for matrix multiplication?
So I haven't looked closely into the AMX instruction set simply because I'm not even sure if I have anything that properly uses it, period. But I would hope that's an operation. So that's one of why I understand the reluctance to put permutations and shuffles, because ARM has explicit transpose instructions to help out with this, whereas x86, you have to do weird things. But yes, I do hope that those actually work, and that would help out a lot.
Yeah, so yeah, I think that's very interesting use of matrix unit for non-AI HPC
Yes,
bugs.
I just hope the penalty for using it doesn't downclock it like AVX 512 used to.
I hope, yes, too.